Yes, as said, the title is about the subspace-based detection method and its application during a lab test, with the final goal to apply this method on offshore structures. Maybe. Here we go, thanks. But I will not focus so much on the method and also not on the lab test itself, but more I would like to give you a view about the way we use to verify the usability of the method or of the vibration-based method in general, to the usability of this method for an application on real structures. We did the classical, I don't know where to, is this? I'm sorry, I've just put the wrong button. We did a two-step strategy. First, we have this lab test, and to figure out how the indicator or the feature reacts to different conditions. We optimized the sensors network. We looked at different parameters of the method, but also of environmental conditions. And then we, in the second step, we numerically modeled this lab test structure and reproduced the results, or tried to reproduce the results in a transient analysis, where we just to figure out if we are able with our model to reproduce the lab test results. And finally, with the with this assumption we have learned of in this stage, we go over to a modeling of a real structure, thinking of different, of course, of different assumptions like damping, etc., and try to model the structure as good as possible. Some words about the lab test. Here you see the lab structure is a classical jacket-like steel frame. We were able to insert artificially damage by losing bolts. We were able to excite the structure with different possibilities, like with this electrodynamic shaker. And we were also able to load the structure cyclically by this load unit. We use acceleration sensors for sensing. And after some tests of the method by loosening bolts, we finally did a fatigue test where we loaded the structure with several thousand load cycles with this load unit here, and we changed this gusset, and we artificially induced here a notch. So we were supposed that the crack will occur here, and we also monitored this area here around with strain gauges to figure out the damage in an early stage. This is actually the result of the fatigue test. In this diagram you see here, these red dots are actually the vibration test, or the SSDD test, the indicator of the damage, and the blue lines are the load cycles, which are took us everything a few hours. You see here that you have steady increase of the indicator of the feature, but in the reality we couldn't see the crack on this gusset until I think here, where we detected the crack, but it was not on the supposed place, but rather in an unexpected location on the foot of the structure. So we are also behind, so we haven't seen it for a long time. And we continued with the test, and the indicator increased, or we could see that the damage increased even, and then it dropped down after another 6,000 load cycles, I think. And the reason for that was that a second crack occurred in the second leg, and the vibrational characteristic is then more than in the reference state, so the indicator dropped down. The diagram up here is just all the load stages here are the mean values are in this bars. Yeah, then we, as I said, we modeled the lab structure, classical with beam and shell elements, mostly beam. Only the area of the damage for a higher resolution we used shell elements. Damage was induced by dilating couplings, and we inserted then contact elements to have a correct opening and closing of the damage. We validated the model by experimental modal analysis and put in stochastic input in it, and then we made a transient analysis of about 100,000 load steps. That's where I think, if I remember right, 40 seconds of a time signal we artificially created. So, and we did this 50 times and 10 times with a different damage state and 40 times in the reference state. And then we use the stochastic subspace damage detection method on each response, and this is actually the final result of the numerical analysis. And as you can see, in the beginning it's not quite the same, but then it has the same characteristic. Also, the drop of the feature after the second crack could also be reproduced by the numeric analysis. Finally, we did then the numeric modeling of the jacket structure, or the support structure of an offshore wind turbine. I mean, you see only a part of the structure, of course, with the tower. And as an input for the transient analysis, we used a record of wind or of a structural response we recorded on the top of a real wind turbine, and use this here as an input for lots of different wind conditions. So we have different stages there, and then we use the transient analysis with different circumstances, and here you see the result for a sensor setup with all four 3D sensors above the sea level, which is quite useful because it saves cost for installation and maintenance of the sensors. And we are not able to detect damage in an early stage, but approximately with 30 nodes, which is approximately 80% of the total stiffness, we are able to detect damage, or at least in this numerical analysis. And the other diagram up here, or on the right side, is we kept the number of nodes or the damage even or the same, but changed the wind, and we with an increasing turbulence intensity, we use this method, and as you can see, it's growing up to a special wind, and then the result is not reliable anymore. And this is because in the real structure where we recorded the wind, the turbine, or the cut-in wind speed was reached, and the turbine went into rotation, and so we don't have this classical stationary system anymore, and this this method doesn't work reliable. So the conclusion is that if you use this method on wind turbines, you should have the turbine in a parking position. So that's actually all I have to present. To conclude, I think it's important to verify our methods, to give the owners or the authorities, to convince them of the possibility or of the value of structural health monitoring. And the best way, of course, is to have case studies with real damage to show that it works. But if you do not have this, or only in a limited number, as Mr. Vance said yesterday, then we should think about using numerical methods to verify and validate the vibrational or the structural health monitoring methods. Even if this is a simple way, we can introduce also uncertainties in the modeling, and going more sophisticated modeling is probably necessary in future. Okay.
Thank you.